So, students, welcome to lecture number 2 on this course on material informatics. So, first we will see whatever we have done in the last lecture. That means I will start from the end of the last lecture and explain you why we are discussing different examples to make you believe that design of materials or selection of material for a particular design is very important purpose, and normally it is done by some calculations or certain set of equations. That is what is the way it is to be done. So, we are discussing about the first topic, that is on introductory concepts, general introduction that I have given in the last lecture. Some more will continue today, and we will move into then statistics and regressions. But before we talk about statistics and regressions, we must discuss about the machine learning and AI. So, we will do that, and then we will move into the statistical aspects as well as regression at the end of the lecture today. So, as part of this general introduction, we have to first discuss about why material discovery is important and how material informatics can play a very important role in accelerating the material discovery. That means making the material discovery fast or happening it at a much faster rate. So, that is the main aspects, and slowly we will build into the machine learning models or machine learning aspects of these. So, first example I gave you on the materials for table legs, and we said that we want to find a lightweighted legs for the table, when which you have a top, you have a flat sheet of toughened glass, and these legs basically support the weight of the glass as well as of the anything you keep on the top of the table, and legs must be solid, must be slender, must be unbraced and cylindrical in shape. And then we have done some set of calculations in the last lecture. You can go back to it and show you that the material which can serve the purpose for these legs is basically what is called carbon fiber reinforced plastic or carbon fiber reinforced plastic. This is the material we can use for the table legs, right? That is what we showed you in the last lecture, but details you can see from the book of Michael F.S.B., which is on material selection and mechanical design, and this book is, as I said, everybody needs to read if you want to do material design or you want to design something where material aspects is very important. So, I do not want to go in details of this, which I have discussed in the last class, and I showed you how we can use this concept. So, now we are talking about the second example or the illustration number 2, and we talked about it, about the energy efficient clean walls, and by clean I mean certain kind of furnace, right? And these furnaces are used to make certain kinds of things, like most important thing is the brick. If you want to make brick from the mud or something, and they are green bricks, and those bricks needs to be fired, and this firing is done inside a kiln, and therefore the kiln needs to be heated up. Now, two important aspects in this kiln: it is a closed chamber. So, therefore, if you want to heat up something and you want to minimize the energy cost, you have to keep remember two important aspects. One, the heat loss by the conduction to the walls of this kiln must be minimized, right? That is very important, because if you are losing more heat, that means you are spending more energy. So, first goal will be to make the walls so much insulating that it does not allow heat to be conducted away. Second important aspect, inside wall of the kiln, which is heated up, right, and temperature increases something like about 1000 degrees Celsius, the inside walls needs to be made such way they can absorb as less as heat possible, right. So, these are the two important aspects. So, that is what I wrote. The part of the cost is the energy lost by conduction, you see here conduction because of the clean walls, and it can be reduced by choosing of the wall material which is of low thermal conductivity, and also making the wall thick. Now, rest of the cost is what? Rest of the cost is because if energy used to raise the temperature of the kiln, and it can be reduced by choosing material with a low heat capacity, because inside wall of this clean has to be made such way that it can absorb less amount of heat. So, therefore, that requires you to make the material which will be having low heat capacity, right. And now it can also be reduced by making the wall thickness small as possible, because as you make it thicker, more mass, more heat is absorbed. So, these are the two contradicting aspects. In case of loss of heat by the conduction, you need thicker walls, okay, but in case of absorption of heat by the inside wall of the clean, you need thinner walls. How to choose the material, or how to choose the material index, so that we can capture these aspects in the design goal. That is what it is, the important aspects. Let us go back to the board and discuss about it. Okay, I already made these pictures in the last lecture. I am telling you again. So, you have to understand that this is the clean and it is electrically heated, as you can see here. Inside temperature is Ti, outside temperature is T0, and the wall thickness is W, and the material of these walls are actually insulating, that means there is a very low thermal conductivity. At the same time, inside wall which absorb a lot of heat should be made up of low specific heat materials. So, there are two important equations you need to consider. One, the heat loss due to conduction, which is nothing but a Fourier's law, that is equal to Q1 is equal to minus lambda dt dx in a one dimensional case, and this dt is basically Ti minus T0, and x is your W, that is the thickness of the wall, right. This is what is equation number 1, which is basically heat loss due to conduction to the walls. Second equation is heat absorbed by the clean wall inside these walls. Actually, this is nothing but Q2, this is equal to Cp rho dW. Okay, rho is the density of this material which is used on the clean walls, and the temperature difference divided by 2 is what is considered as the temperature difference. Okay, so therefore, total heat is consumed is because of these two aspects. One, because of the heat loss, other is because of the absorption heat in the inside the clean wall, that is equal to Q1 plus Q2, that is equal to this. So, now this is what is my master equation. Okay. So, I put this equation as a number 2 and this equation as a number 3. How do I find out the the two things? One is your clean wall thickness, other one is the choice of the material. These two aspects I need to find out very well, right. These are the two important aspects you must have to remember. So, how do I do that? Let us do that. Okay. So, first is very simple. Wall that is too thin will lose a lot of heat, as you understand, because of conduction. If you make it the wall too thin, it will lose more heat by the conduction. At the same time, if you make the wall too thick, it will lose less heat by conduction, but it absorb more heat because of the heating up, right. So, therefore, one way to do this, solve this problem is to make the optimum thickness simply by differentiating the first equation. So, differentiating the second equation or the first equation with respect to the wall thickness and equating to 0. So, if I take the second equation, that is 2, and then differentiate with respect to W, what do I get? I get Cp rho W gun, okay, and this is Ti minus T naught by 2. That is what I get, right, if I differentiate this equation, right. And so, differentiate equation with respect to W, and then equating this results to 0, right. So, as you can clearly see, if you do that purpose, what you get? What you get is very simple. Let me just do the calculation for your purpose. What you get? Very simple. So, I get Ti minus T naught is equal to, this is equal to 0, okay, correct. So, that is my Ti minus T naught. Now, I think I am doing some mistake, let me check it. No, it is not that. So, this is my first derivative. So, this optimum thickness can be obtained simply by putting both of them to 0, and the first one is what? dq1 by dw, that has become lambda Ti minus T0 divided by W square, right. That is what you should understand, and this will be minus will be plus, okay. or this will be minus. Okay, that is what it is. So, now if we equate these two, what you will get? You will get W equal to twice lambda, correct, twice 2 will come there, twice lambda T I have not put T here, yeah, this should be T, yes, Cp dt, right. This T, small t is coming from time, this T has to be considered. So, 2 lambda T divided by Cp rho, you can do that yourself, that is the optimum wall thickness you can obtain. You can make these two equal dq1 by dw equal to dq2 by dw. These two will give you equation like that. So, this is my optimum wall thickness, that depends on all the important parameters, thermal conductivity, Cp and density, and obviously time. Time is decided by the what is the heating rate, right. So, this you can see this will be equal to nothing but this will be equal to 2 A T to the power half. A is a thermal diffusivity, let me write it here, diffusivity, that is equal to lambda by rho Cp. Okay, that is what is your thermal diffusivity is the definition. So, that is it. So, therefore, the important parameters which will decide the wall thickness is what is known as the thermal diffusivity, right. That is what is the critical parameters in this case. So, you have to choose a material which has a very low thermal diffusivity, as low as possible. That is the prime aspects you understand from this. Okay. So, your first and important parameter is a thermal diffusivity, that is your design parameter. Okay. That A, what I have written is your design parameter on the board, you can see there, that is your first important design parameters. Okay. And you want to understand that if once you write 2 AT, that is a dimensional number, A is a diffusivity. So, diffusivity as a unit of is basically unit of, so it is a unit of distance. Okay. And because it is multiplied by T, that is why time will vanish, because meter square per second, and time is unit of second, right. So, the time unit and this unit of A will cancel. So, what will have basically meter square, and if you take a square root out, it will be meter. So, it has a unit of meter, that is why W become that one, exactly units are balanced on the both sides. And so, and it is a very important parameter for a material, because it tells you the distance heat can diffuse in certain time, that is what the diffusivity means. It is same as a chemical diffusivity, correct. So, now this is the first thing you understand, the W or thickness of the wall will depends on the thermal diffusivity of the material. So, if you want to make a very thin wall, your A should be as small as possible, correct, that is what the key thing. And if you want to use a material which has a higher thermal diffusivity, then your W has to be big. So, your decision of the choice of material depends upon what kind of A values you are using, right. Now, second important aspect is what? So, Q, and then Q has to be minimized, right. So, if you can minimize the Q simply by minimize this lambda rho Cp actually, that is the prime important aspects. Now, go to the next important aspects, what is the thing. So, as you can clearly see, the first and foremost important aspect is you have to look at is the thermal conductivity versus this chart. Let me see whether I have missed it. Thermal conductivity versus thermal diffusivity chart, and then you have to select the material which has the lowest thing. So, as you see bricks has normally thermal diffusivity is very low, the parameter which is A is very low, and therefore, you can use the thickness, you can calculate the thickness also. You can use concrete also, but concrete is not a good idea. Concrete can withstand high temperature, but it is has a much lower value of A. So, you need thicker, thinner things. woods cannot be used because it can burn actually, but it is insulating material. You can also use solid elastomers or polymer material people use for that, but it can go up to 150 degrees Celsius temperature. So, as such the choice of material should be brick. Okay. That is what one has to use in this particular case, or energy clean efficient walls. So, this is for the illustration number 2 which we have discussed. Now, let us also discuss something about process requirements. Okay. In design of materials, sometime you also look at what is the particular processing condition or process route you will use to make the object. Okay. So, one aspect is the choice of material, other aspect is how do you make it, right, or manufacturing. So, in this case processing requirements is what is to be decided, right, and we can also do that with the same way as Michael Ashby has given in his book. So, let us talk about example of fans in a vacuum cleaner. As you know, you must have seen the vacuum cleaners. Vacuum cleaners have fan to take away the moisture as well as the heat, as well as the heat also, right. That they are designed to be very cheap, very cheap, quiet and efficient. Probably in the order of cheapness first, quiet, will not create much noise, and also it must be efficient. So, key to minimizing the processing cost is to form the fan to the final shape in a single operation. That is the prime aspects. If you can form the fan in a single operations, that means you can avoid secondary tertiary operations, then you can achieve the best possible, the cheapest possible way, not the best, but cheapest possible way. And that is what is the main idea. That means selection of a single process that can meet the specification on the precision as well as tolerance without much machining or finishing operations will be the one which you select. So, you want to make a fan where of the vacuum cleaners, this certainly looks like, and material is normally used is nylon, as you know, it is a polymer. As many of you seen the fans which are placed in the computers or the laptops, they are also made up of polymers, they are made of basically nylon. Shape is 3D, mass will be very low, 100 to 200 grams, and minimum section is about 4 millimeters. That is what the thickness of these blades is, minimum section. Precision is not very large, it is about plus minus 0.5 millimeters. Roughness is also very low, less than 1 micron, because you want to have a quiet fan which is not make a lot of noise, and you want to produce large quantity, almost 10,000, and your objective is basically minimize the cost, correct. So, this is the table which is important when you try to design something, whether it is a material or an object, or you want to make a process also, that is what you have to make it. So, now if you look at, there many processes exist, shaping, joining, finishing I have written here, you can see here. In shaping you can have sand casting, die casting, you can also have blow molding, compression molding, polymer casting, resin transfer molding, so many things, right. Which one will you use? See, this is not a metallic component, so why to use casting techniques? Casting techniques are not required. You can see here casting techniques are good, casting, forging, extrusion are good for metals and metals actually. And for ceramics you can use electromachining, conventional machining, injection, all these are powder metallurgical processes. So, here the fan is not made of ceramics, so why to talk about it? It is not made of glass, it is not made of elastomers also, it is made of thermoplastics, nylon. So, we can use various kinds of process starting from conventional machining, injection molding, blow molding, compression molding, rotation molding, transfer molding. That is what my choice, this is what is mentioned here, you can see here, right. So, now which one you will select? If you talk about injection molding, it meets all design requirements. Compression molding may also meet all the design requirements, then which one to choose? You have to consider the cost, right, cost is the most important aspects, right. So, as you can clearly see that there are always many other considerations. Most important question is the capital investment, skill, overhead cost and other things. So, it is very clearly chart shows the best possible process is the injection molding, that is what is used. Most of the fans which are used for this kind of purposes, like in case of washing machines, or in case of vacuum cleaners, or in case of computers, laptops are basically made by these compression molding techniques, which is widely used. So, here we are comparing all kinds of things, we are comparing the different processes, and as you said, this has to be single process. So, we do not want to talk about joining and finishing process also. And if you want to use a metallic fine, it will be very heavy, it will be costly, has to be cast, machined to get the surface thickness, so that most important thing, it will be costly and heavy. So, you cannot use it, that is why polymeric ones are widely used. So, this is how actually a process can be selected. So, I am just telling all of you to read this book of Michael Ashby to understand more of these design problems. So, what you understand from these examples in a nutshell? You understand that these examples tells you that this is the way most of the cases designs are made. First, to understand the particular situation where the material will be used, which way the material is processed, and then we can use set of mathematical equation is required, or you can use our own concepts, analogical aspects to decide, make a decision on design. But that is what is done formally or traditionally, right? But that is not the best way, as you understand. That is why we are talking about informatics. Can you use data to change the design concepts? Well, that is what is the main goal of this course. I just thought of giving the example so that you can actually get an idea how designs are done in the real world. So, in that case, material informatics becomes very important. What is material informatics, by the way? It is a field that uses data, first thing you understand, and many computational methods. Why? To accelerate the material design, discovery, development and deployment. So, we want to make it fast, we want to make design things very fast. Not only design, we want to design, we want to develop, we want to deploy, everything we want to make fast. So, what do? You use data and use the computational tools. So, in the nutshell, this is nothing but a combination with data science and the computational science, right. So, first important aspect will come to your mind is data. Data are obtained from material science and engineering subjects, because we are talking about material design or material informatics, correct. So, therefore, your data are coming from material science engineering, and your tools are coming from computer science engineering, okay. And then you are using information science to process it. So, it is an interdisciplinary field, right, where you use expertise in computer science, statistics, mathematics, engineering as well as concepts of physics. There is a true sense, it is an interdisciplinary field. One has to know good at many of these, right. Obviously, one cannot good at everything, but at the same time, if you have some knowledge of material science, you can learn the aspects of computer science, machine learning, statistics as well as physics principles to make you an expert in data science. So, basic approach is simply by understanding the whatever knowledge available, okay, that is what comes the picture. See, if you simply talk about data, data alone cannot be made your life good, because you have to connect data with the physics, data with the knowledge which are available in the real world or in the domain where you are expert. So, therefore, whatever knowledge available in the material science can be used to study the data in terms of experimental data or the simulation data. This is much better than the conventional technique of trial and error, or even the one I shown you, the design, the way it is done in traditional manner. Trial and error obviously is not a good idea at all, but one has to also think about how can you do better job than this the examples I shown you. So, that is what it is. And why we do material informatics? Well, this is what is shown you here. The search of new material is very important for the society as well as technology, right. And this is always required if you want to have a new gadget, new material, new technology for your purpose. Okay, let us talk about various kinds of objects we see day to day life, correct. If we look at clock, the clock has undergone a massive change. from analog clock to digital clock to even smartwatch, right? Many of you are wearing the smartwatch. It can record your body parameters or physical parameters. So, there are biosensors built in, right. So, it is not no longer a watch, it is basically a machine which can give you a lot of important inputs from your biological processes, from your physical parameters as well as your activities. So, you need different materials for that, for all these biosensors. So, therefore, such a material is always on, new material, advanced material, it will be always on, whether today even 100 years after also, when we are not be here in this world, still it will be on. So, therefore, it is better to understand the underlying science or engineering which govern the behavior of material. That is the key aspects. If you know that, then you can design material faster. And informatics or data science can be made to use to discover new materials in a much better way. That is why we are studying this. So, now if you know, there is a field called integrated computational materials engineering, or what is called ICME, and one can look at this book on material informatics, and this is nothing but combinations of experimental data, physical simulations and computer simulations together. It is basically combination of these three things. Data are obtained from there, experiments, simulations, physical simulations. One can do physical simulation in lab also, right? Many of us do that. And then you can use this data in combination with machine learning and data science to accelerate the design of materials. That is the concept of ICME. In future, I may teach a course on ICME later on in a detailed aspect, but this is what is the key aspects of ICME on which the Material Genome Initiative, what is called MGI, Material Genome Initiative by US in 2011, MGI, it is called MGI in the literature. It is a US initiative 2011. It was started with a huge funding, and that is the prime principle is the material things. So, what is the framework of this? Well, you can have data come from literature, experiments, simulations. First thing you do is some thermodynamic calculations, correct? That is the basic thing. To understand phase stability, thermodynamics is very important, and then after you got these thermodynamic calculations, you have to see how it can be made. If you are using solidification or casting as a route, then you have to use cell solidification simulation model to do that. If you are using deformation route, then you have to understand deformation micromechanism principles to do that, correct? Then you can actually get information on microstructures, what is the end microstructure will form, and all this information together will allow you, to understand what is the optimum alloy chemistry and also what is the optimum synthesis route, correct. So, these two are your requirements to be understood, okay. There are many softwares available like Thermocal, FactStage, Pandat, OpenCalFAD, all of these will allow you to do thermodynamic calculations. These are nowadays routinely used. You can also do microstructural simulation using MicRes or MicroSim. These are all softwares which have been built up. So, these allow us to go into from the top to bottom and do this. So, idea is to have how to connect data with design of materials. That is the key aspects in these things. So, central theme of any material science development cycle is this processing, structure and properties space linkage. How we can connect that? As you know, property will depends on the structure or microstructure, and structure will depends on the properties. How can you connect that? Professor Surya Kalindi has discussed a lot on these aspects. I have taken his slides from his book. As you can see here, this is the central theme. So, how can you use data science to connect these two? This is a dream till, but it can be approach next things. So, just give you before we stop for the next part of lecture, a sketch of steels. If you look at steels data, all the steel data, I have plotted tensile strength versus elongation. It is a banana curve, right. If you want to have a high strength, you have low ductility. If you have high low ductility, you have low strength. You can't do much about it. Can I break away from this? Can I, this is my banana, right? You can see here, this is what is the banana curve looks like. You can see that this is a banana. So, can I break away from this? Go here, go there, go there, right? I can have material with high strength and high ductility. Is it possible? Yes, it is possible, and that is what actually material informatics can allow you to do that. So, let us talk here for the first part of the lecture 2. We will come back to the second part of the lecture, okay, where we will discuss much more aspects of other things. Thank you.